Good morning, everyone. I'm Matt Harmon from the University of Sheffield, and I'm going to be talking about a TACKINESS test which I developed. This was part of my PhD, which is funded by the Rail Safety Standards Board in the UK, and this section of work was actually done in collaboration with Stanhope Seater, who are a test rig manufacturer from the UK as well. So I was at the Severn Valley Railway, which is a heritage steam railway in Birmingham, or near Birmingham in the UK, and I was looking at different grease applicators and how the grease is pumped from the reservoir next to the track, through the hose and out through the applicator. And you can see the grease bulb standing in yellow there. So yeah, I was looking at how the wheel interacts with the grease and how it picks it up. And so I installed a camera next to it, and you can see in this diagram before, you've got the wheel coming across the applicator, and as the wheel passes over, you get these big long strings of grease forming. So that led me to look at the sort of down the tackiness route, like does the ability of this grease to form strings, does that impact on the pickup of grease to the wheel, and therefore then lead to better lubrication of curves? And would a more tacky grease, so a grease which produces longer strings, would that lead to better lubrication or not? So I visited a grease manufacturer, and their test for tackiness was this type 1. So they get a flatbed, blob of grease, and a person just stands there with a spatula and just goes, yeah, I reckon that's quite tacky, or I don't think that's quite tacky. So I thought there would be something more scientific that could be done. And there wasn't a test standard for tackiness, although I believe one is being developed at the moment. But I used a UMT machine due to its ability to be modified. Got 2 samples made out of stainless steel and put a blob of grease between them. Compressed the 2 samples together and then measured the force as you retract the upper one away. Which you can see sort of the beginning of the test here with the grease blob in between. Now clearly this isn't representative of what happens actually out on track, but the idea is that it gives you a really quick, simple test which you can do to get like a comparative result. So you won't get any real values from this, but you will get a comparison from one to another, or from different temperatures and things. So this is the example graph you get. So you initially start off with the grease in compression. The initial phase is as that compression's been relieved. Area B is as you start to separate the discs, you're also overcoming the resistance within the grease. And it's area C, so from the peak all the way down to as it tends to 0, that's the energy that is required to break the grease strings, and it's this that I'm calling tackiness. So we use a MATLAB script to work out that area C. So initially I had to do some preliminary data, so work out what actually parameters to use. So this is just showing how the work required to break the grease strings changes under different parameters. And so again, sort of the compressive forces are low, the retraction speeds are quite low, but this isn't meant to be representative of the real rail interface. It's more meant to be just a comparison from one to another. And you can see how compressive force increases and then decreases. That's due to, as you compress the plates together, you basically get more cavitation occurring, which breaks the grease strings faster, so they require less work. And for the initial grease amount, if you use too much, basically what happens when you squeeze them together, the grease sort of squeezes out the side. So there will be like a finite amount before that curve there basically just flattens off. So I chose the parameters which would basically make the work done bigger to reduce the error. And you can see from figure D there that the values sort of hover around they're quite repeatable over a number of different tests. So I got as many greases as I could find in the lab. These ranged from sort of household greases, which you'd normally find, right way through to actually greases which are used on the UK network. And you can see there's quite a large variation within them. So this shows that the test can tell the difference between different greases, and as well as there also is a roughness effect. So the specimens were made from at different roughnesses, and you can see that slightly rougher slightly rougher specimens give you require more work to break the grease strings. So greases 7 and 8 were different formulations of a grease which is used on the UK network, and using a scaled wheel rig, which you can see in the bottom right corner. So this is a top-down photograph of it, and you've got a scaled wheel which just rolls along a track, well, it rolls along a section of rail, and we can put different applicators next to it. So on this test, you pump out amount of grease, you roll the wheel through, and you measure the amount of grease which is transferred to the wheel. And from those tests, you could see that grease 8 gave you a much bigger pickup than grease 7, and correspondingly, in the tackiness test, grease 8 has a larger tackiness as well. To try and work out how the resolution of the test, I added in different amounts of tackifier additive. So I used quite small amounts, and there is a small upward trend, although the error is quite large. This is mainly due to the amounts you're using. If you've only got 0.8 of a gram of grease, and then you're trying to add 0.75% of that to it, it can be quite hard to control the amounts. Yeah, so the resolution is quite good, but not quite down to these very, very small amounts. So this doesn't happen on the railways, but I was sort of more thinking if this test is used by a grease manufacturer, they might want to use it for different applications. So on this, instead of just compressing the plates and rising them up, during the compression stage, they then oscillate very, very slightly, and this sort of works the grease. This was sort of done through, anecdotally, if you work the grease, it produces more strings. So I did two types, one where during that oscillation you're reaching the peak force each time, and type B where you're not quite oscillating as much, you're not reaching that peak force. These are results from that. So you can see for type A, where you're reaching that peak force, you basically reduce the tackiness if you work it more. I think this is just because you're shearing some of the polymers, some of the polymer chains inside the grease each time you're working it. Whereas with type B, you actually get an increase in tackiness. For the more you work it, you create more strings. Eventually, though, you get to a point where you start to decrease again, and this is, again, due to that cavity. If you work it more, you're aligning the molecules of grease inside, you're aligning the chains inside the grease, and then when you go to retract it fully, you basically get more cavitation occurring, which breaks those strings. So basically, create a test which can differentiate between quite a lot of different greases. It can detect different levels of additive, but this has sort of got a star next to it because they're very small amounts. It won't be able to, just it gets kind of lost in the error. You can tailor this approach to different applications. So if you had it at the end of a production line, you can use some quality control, or you can even optimize sort of different greases for not just the railway industry, but for others. And I have linked the performance in the sort of the small scale unrepresentative test to actual pickup as well. Just like to touch on some further work which I've done more recently. So, because the modular nature of the test rig that I've used, it is possible to add a sort of temperature humidity control. And I've also, with the help of LB Foster, extended this work into top of rail friction modifiers. So, and you can see in the graph there that from done the exact same test on tackiness, and then done a pickup test using a scale wheel rig, and also used the full scale rig which Steve Lewis presented yesterday. And you can see the same relationship from the three different friction modifiers, where sort of B, friction modifier B, which is a more sort of tacky friction modifier, gives you more pickup in the scaled wheel rig and full scale rig tests. So this shows that you can use this to sort of give you an indication of further of pickup in the actual real rail interface. and it can be used by either manufacturers to design and optimize their products, or can even be used as quality control. So as maybe an infrastructure manager, you know that the project you're getting meets whatever requirement you've set. So thank you for listening.